and welcome back to Geology. I am Robert Lopez, and today I want to finish off with sedimentary rocks and talk about sedimentary structures and some depositional environments. Now, one of the first features we see with sedimentary rocks, in fact, one of the most conspicuous features of sedimentary rocks are layers, strata. They're these sedimentary beds. So one of the features we'll talk about is the formation of this bedding. And we call these beds because some physical process is said to lay down the sediment, right? So this is lay down, and each bed represents a change in the energy or the environment. It could be near shore, farther offshore, sea level could be different. Another view at these layers, these strata. So remember, stratigraphic is the charting of the strata, and remember, strata means layers, right? So one stratum is one sedimentary bed. And so the Grand Canyon, the most conspicuous feature here are the layers, the strata. It's the Brighton shale, the mauve, the red. So all these, there's limestones, there's shales, there's top-eat sandstones. So the sandstones represent some beach environment, some marine sand near shore, shallow water. Shale here, Brighton shale represents a little bit deeper water, lower energy. The limestones, mauve and the red wall limestones, well, those are deeper water, right? Very quiet, deep waters, mostly planktonic organisms. So certainly just in this one section here, we're seeing environment changing, the conditions changing, the energy changing, right? Which leads to different rock formations or beds. And note that the contacts between beds are called contacts. They're the divisions between these beds. Then other sedimentary structures besides bedding include these things called ripple marks or dunes. And the key thing about ripple marks and dunes is it signifies a process. And we can get for example, like here, these ripples, we know we have waves that oscillate back and forth, right? So these seem like they're uniform ripples, which means that the water was moving, sloshing back and forth like in a tide or waves coming in here, right? So this is forming at a beach today, but here they're preserved. So when geologists see these types of ripples that are lithified in an old rock, we know that this must have been some shoreline, because that's what we see today. Later on, when we start talking about geologic time, I'm going to talk about this principle that we use, that geologists use, that's called the principle of uniformitarianism. And basically the processes we see happening today, the laws that govern the universe have remained the same, right? So here we have a modern coastline. Well, here is a coastline that happened millions of years ago. Well, the same physical process, same laws governing the waves millions of years ago are also working today, right? So we can use what we observe today to interpret the past. Yeah, so crossbedding, the key to crossbeds is you have a dune migration. So these dunes are actually moving across the surface. This dune will eventually, the wind will blow it and it'll move across the surface. And so the dunes, crossbedding, so you can see these foresets here, those are the crossbeds, but you can see these are individual beds. So there's there's several. There's 1, 2, 3, 4, 5, 6 beds here, right? And the crossbeds are the foresets that are at angles to the overall nearly horizontal bed. Now, what we're looking at here, you can see this dune is migrating over time. Is that the tops of the crossbeds are always cut off. See how these kind of end at an abrupt line here? Because there's erosion going on when the next crossbed comes over it, right? And the bottoms always curve down. See how they kind of slope down? They slope down to meet the bottom. So the bottoms are said to be tangential, where they slope down, but the tops are said to be truncated because they're cut off by the next series of crossbeds that are coming over. And those are what we call paleo or ancient up indicators. So they tell us which way was the old up direction, because if there could be some folding or faulting that occurs here in the future, the strata may be overturned, turned upside down, and we could determine whether or not these beds are overturned. Later on, again, with geologic time, we'll have to deal with that. So again, dune migration. The second thing that the crossbeds are telling us is that the direction of the current, right? So see the current going in this direction? Note that the crossbeds slope in the direction that the current is moving. So in this case, since the wind seems to be blowing in this direction, so they're all sloping in that direction. If they're sloping a different direction, that means the current would be blowing the opposite direction. So let's see, let's go back to this slide here. So you can see in here, we have these, the current must have been blowing, yeah, so you can see the direction was blowing in that because they're all tilted in this direction here. So, and see how they're kind of sloping down. So up is this way, and the current was going from left to right here. We've already talked about turbidity currents and turbidites, right? So graded beds. The key thing about these is they're coarser on the bottom, finer on the top. Coarse to fine, coarse to fine. And again, they're telling us a paleo up indicator, right? We know if this strata is overturned, then we'd see an opposite direction here. So they're useful for figuring out whether units have been overturned or not. And then another surface feature are these mud cracks. So these indicate where there's it's exposed to air, there's evaporation, and you get these mud cracks that are forming. Here's some old mud cracks right in here. Also, fossils can be useful for determining the environment of deposition. When I look at a shell bed, I realize that shells occur near shore, right? They're not going to be in the deep, deep ocean, right? So in fact, there's two words I want you to know. One is pelagic. Pelagic refers to deep waters, waters that are beyond the continental shelf, the slope. They're deeper than 200 meters is really what we say, out in the abyssal plains often. Whereas neritic waters are near shore waters over the continental shelf. So when I see this limestone of brachiopods, I know that this is a near shore or neritic environment, right? So that's how they can help me determine the environment in the past. And so that's where we want to get to next, these depositional environments, where the sediment comes to rest and accumulates. And again, this is a key to interpreting the past, right? So, remember I mentioned earlier, we're going to have terrestrial environments, right, which are non-marine up in the continent. So there could be glacial, mountain front here. There's arid environments. There's fluvial or stream environments here, lake environments, right? And then there's the coastal environments, which include deltas, estuaries, marshes. And then there's marine environments, which include the continental shelf, the slope, these submarine canyons out here, and abyssal fans, turbidity currents out here, and then obviously the deep ocean in the abyss. So looking at some of the terrestrial environments, so what would I expect to find in a glacial environment? Well, for starters, I see it's poorly sorted. I got big class and small class all mixed up. And note that they're very jagged. So jagged, angular fragments, poorly sorted. And often the class are going to be scratched because as a glacier moves, the rock frozen in the ice gets scratched against other rock and leaves these grooves or striations on the rock. So I'm looking for those striations as well. And then for mountain stream environments, well, these involve higher energy, right? Higher energy, faster moving water. It can move bigger class. So I'm going to expect boulders, conglomerates, right? And not all of them are rounded. In fact, I may even find some breccias. Remember, breccia would be the angular class, right? So breccias and conglomerates up here, but clearly bigger particles. It's going to take a while for these to get smaller as they disintegrate, going into the lower energy environments of a river valley farther down. And so remember, fluvial refers to this stream environment. And other environments, alluvial fans. So the definition of alluvium is sediment transported by water, right? So this is obviously being transported by water, but it's pretty dry now. This is Death Valley. They do get rain, and when it does rain, it does do quite a bit of erosion here, right? And so alluvium is sediment moved by water, transported by water. So an alluvial fan is where the channel changes from a narrow valley here, where there's more energy when the water's moving through here, to a much wider valley out here. So the stream loses energy. So when the stream is moving through here, it's carrying particles. It can move them, and then once it enters here, it spreads out, and the water loses its energy and drops those particles here in this fan-shaped pile. So again, we're narrow mountain valley or narrow mountain stream opens up to a much wider valley. Desert environments, right? We'd expect to find playa lakes, large sand dune deposits with large cross bedding. Mud cracks would be common in this area as well. So again, those evaporite minerals. River environments, remember those are the fluvial environments. So we see silt and fine sand, channel deposits. So here, what a geologist sees here, I see a channel deposit right in here, channel deposit, and some younger soil up on top here, younger floodplain deposits. So again, telling us that this is a fluvial or river environment. Here's some people for scale down in here. Then as we look around lake environments, the word we use for lake is lacustrine. But lacustrine environments, here they're quieter water. So note I have quiet water, so I'm going to have finer particles, mostly mud size, and they occur in these laminations. Then as we look at delta environments, so now we're looking at coastal environments. So one thing that happens with deltas is that, in this case, this one looks like it's prograding out into the sea. And so you'll see that there'll be these older beds, also called foresets, like cross beds, but they always slope toward the ocean basin, or the basin it's collecting in. And you'll see that we'll have coarser material near shore, finer material farther offshore. When we're in the marine environment, how do we know whether we're pelagic or we're neritic? Remember, pelagic is deep shore. Well, one thing I know about the pelagic, you won't find sandstone in the pelagic environment. You will find shale out there, but not sandstone. The fact that you have sandstone mixed in with the shale here tells you you're in the neritic or near shore environment. So that's how you can use combinations of sedimentary rock to tell you where the environment occurred. I know this was not very deep water, maybe 100 meters, 140 meters at the most offshore, but certainly closer to shore than on the continental shelf. Then as we look around here, obviously I also talked about these different environments varying with climate. So in the tropics, we get carbonate platforms, and where activity of CO2 is relatively low, and we're producing, in fact, we're not producing any carbonic acid. In fact, we're kind of have low concentrations of CO2, and which allows precipitation of calcium carbonate, right? Especially in these lagoons where sunlight is evaporating some water, and you get concentrated calcium and carbonate. So not only do you form, calcite sands, calcite muds, but also you might even get some gypsum and halite forming in some of these areas here, right? So that's some of the shallow water carbonate environments. Deep water environments, so those would be the pelagic environments. So here, these are the White Cliffs of Dover, which are in England, and they're composed entirely of these coccolithophores. Coccolithophores are small plankton, planktonic algae that does photosynthesis, but these guys make shells that have calcium carbonate. So these are chalk. These are all cliffs of chalk, and so being deposited in quiet waters, small organisms sinking to the seafloor, making these calcareous oozes and making this limestone chalk. And then there's sedimentary basins. One of the key things I'd expect to find in sedimentary basins in continental settings is, since we're eroding probably a granitic source, I'm going to find arco sandstones in here, right? Probably arco sandstones, probably poorly sorted, especially if it's the Rift Valley here. When I'm at a passive margin, remember I'm looking for quartz sandstones out over here.